for the project is going to be sent to you. I'll give you the handout later. We'll cover MANOVA today, which will give you most of what you need to do for the project. So may need to do a little bit more next time. And I guess that's it. Okay. So this study is the relationship between experiences of discrimination and mental health among lesbians and gay men, examination of internalized homonegativity and rejection sensitivity as potential mechanisms. Got all that? No. So what they wanted to do was to see whether early experiences of childhood gender nonconformity would lead to experiences of discrimination, and then that in turn would lead to depressive symptoms.
Experience of what?
So they had a scale of childhood gender nonconformity, which basically is as follows. Childhood gender nonconformity was assessed with the childhood gender nonconformity scale. Is a 7-item self-report measure designed to assess the degree of gender nonconformity of recalled childhood behavior. Respondents rated agreement from 1 to 7 on a bunch of different items. For instance, as a child I preferred playing with boys more than girls, or for males would be, and the version for men would be as a child I preferred more with girls than boys, etc. Those kinds of things. So they got a score on that. They then got a score on experiences of discrimination, which is to recall how much discrimination the person experienced, and then a depressive symptom scale, CESD.
Were they making specific predictions about what they
Yeah, they're trying to, their hypothesis is that childhood gender nonconformity leads to experiences of discrimination, which then leads to depressive symptoms. And so they want to assess that. Okay.
I don't have this.
We'll get you one in a second. Just start with it.
It's just one time.
Yeah, they did it all at one time.
Here, I can play with this while you're educating.
Okay, thank you.
And it's all scored.
Well, yeah, each of the scales is a continuous measure. Each of the scales is a continuous measure. How do we do this last time? Okay, this one. Yeah, let's just do that.
Oh, and the IT guys are on their way, so.
Okay, well, when they get here, what are they going to do? Well, multiple regression. But the best answer would be path analysis, right? It was one thing that was another.
What is this written here?
Regression to give that.
20 minutes.
how would we do it on a decision tree? We'd have to have a couple of more trees, right? So do you have variables leading to another path or something? You have to have another one. So the best thing to do is just remember if there's one thing leading to another, it's path analysis. So they actually did a more complicated path analysis and got a pretty good fit. So what do you get when you get a path analysis to tell you if it was a good fit? A little review here. Chi-square, you want it to be significant, right? No. Don't want it to be significant. Non-significant means good fit for the chi-square for the path. And then the other one was the RMSEA score. And that one was below 0.04, which is below 0.09 means it's a pretty good fit for the path. So they had gender nonconformity, leading to discrimination. And then they also had some other outcomes too. They had internalized homonegativity, which also led to social anxiety, depression, and rejection sensitivity. So they had three more measures, and the path looks like that. And the weights on here are the beta weights, and the goodness of fit measures. So this is a pretty good model, actually. Those betas are decent size, except some, but most of them are pretty good. And given that this is all retrospective experiences instead of actually measured at the time, it's probably a pretty good fit. That's sort of how this works. Sort of makes sense too. Okay. All right. So I don't know if I can get this working somehow. I'm going to get this Oh, this is on the screen.
Every assumption there is. That's right. Scoring that tonight. Carrying the PowerPoint.
Skill of renders, and we make them through this lecture without checking things. No, it's mine. I'm mostly worried about mine, not yours.
But I can move them over there.
No, no.
You sure?
I'm just kidding.
We'll just clap if you're about to.
Okay. So, anything left over from the last time that we weren't yet, probably? Discriminant was last time. Is that okay? Everybody okay in discriminant? We're going to kind of review discriminant again today because you need it for MANOVA. All right, so MANOVA is multivariate analysis of variance. This occurs when you have some true IVs and more than one DV. You get any model that we had in MANOVA, can be seen in MANOVA. Two-way, three-way, four-way, repeated measures, no repeated measures, all those designs are exactly the same. But the underlying mechanisms are quite complex and involve using matrix algebra. And I'm sure you'll all be thrilled to find out that we're not going to teach you matrix algebra as the mechanism for doing this, because it's a whole series of steps of how to do it. But the formulas for MANOVA, if you see them in another stats book, will be formulas in matrix notation, which means that matrix is a whole series of numbers, rows and columns. You multiply them, you can't divide them, you invert them, you can subtract them, and you do everything you would do for our sums of squares formulas in ANOVA, but you do them with a matrix formulation. And you come up with then a matrix type of an outcome, which is a little different than the ones we're using, even though there are F equivalents, as you'll see as we go. Why would we use MANOVA? Well, 1 dB seldom captures the full picture, and especially in clinical psychology. It's hard to just say we just want to measure just depression, not anxiety, not something else, whatever kind of thing we're doing. Usually we do want to look at more than 1 dB, so that's something we want to do. There is a possibility of using type 1 error to control, using MANOVA to control for type 1 error, or experiment-wise error, sometimes called probability pyramiding, where, remember from the first semester when we would do a whole bunch of different comparisons of the same MANOVA, you would get type 1 error created by that, right? If you did 100 comparisons, 5 alone should be significant by chance. So we went through a lot of trouble last semester to find ways with Bowen-Ferroni's, post hoc tests, plan comparisons to get around the issue of experiment-wise error or probability pyramid. Well, MANOVA is a possible way of avoiding that. The way that happens is you first do a multivariate analysis of variance on all the dBs. If the multivariate statistics are significant, then you're allowed to do the univariate statistics without control for type 1 error. Kind of makes sense. It's kind of a gatekeeping mechanism, right? So you say, I'm willing to live or die by the overall set of dBs being significant. Once we get significance in those, then the chance of that being due to, the probability of that being due to chance is much lower because you got an overall significance. So that kind of controls for the issue of the experiment-wise error. It's somewhat controversial, but it does kind of work, and people sometimes do it that way. The other thing about MANOVA is it captures the intercorrelations among the dBs. So sometimes a bunch of dBs together work better than any one of them would separately. And so you can use the MANOVA to kind of look at complicated situations where the dBs are correlated. And it'll do this for each level of the IV. Also, you can be used to reduce large numbers of dBs into smaller sets like you do in factor analysis. Essentially what MANOVA does is it sort of does a preliminary factor analysis and then tests the significance of the latent variables that it's created out of the many dBs. You can identify dBs that best distinguishment levels of the IV, so you can kind of look among them. And sometimes you can increase power quite a lot. If you have a situation where, let's say you had 5 dependent variables, let's say 5 different aspects of depression, none of them were very significant by themselves, but they all went in the same direction, that combined 5 measures might get you a significant difference between the groups, whereas none of the individual ones would maybe be also be significant. So you get kind of a construct out of that that can be quite powerful, but you have to have thought about it that way. There are some definite disadvantages. If the dBs are not correlated or too correlated, you shouldn't use MANOVA. It messes up. So we want to look for moderate correlations among the dependent variables. Not correlated at all, there's no advantage to MANOVA. If they're too correlated, you're ending up with the same measure basically measured 5 times, so it doesn't work to do it that way. Connie and I think that if you don't really think the dBs represent a good latent variable, if you're not really thinking about them as representing a latent variable, you might just consider using some type 1 error correction instead of MANOVA. There's some choices here that we'll talk about later. So the most common case is, one of you would do in a dissertation, is that you're going to try an intervention let's say one of these interventions to deal with homonegativity in a group of gay men, and you want to try some CBT versus ACT versus a control or something. And of course, you end up with, you're not going to just measure one thing, right? Homonegativity might be your main DV, but you're going to probably want to measure depression. You're going to probably want to measure anxiety, some relationship measure, et cetera, et cetera. So you come in with your 5, 7, 8 DVs, and the decision tree tells you to do a MANOVA, because you have a bunch of DVs in the MANOVA design. But really, those DVs are not thought of working together particularly. You're not going to come out with a single latent variable. So in that case, we think you're better off doing separate ANOVAs and just doing some control for type 1 error, as we'll show you. So this happens a lot where other faculty say, well, the decision tree says do MANOVA, so you do MANOVA. But the MANOVA doesn't really tell you much if you can't think of those DVs working together in some way. And as you'll see, the assumptions are tricky. They're actually the same assumptions in discriminant analysis, but they're hard. So this protection against type 1 error is a complicated topic, but it gives us a good chance to review a lot of stuff from last semester. So take a look at the handout that I gave you. This is too busy to put in a slide, so if you go to the first page of the text, in the right-hand corner is written Hummel, Sligo, Stevens on the top. See that? So this is a justification for using MANOVA to protect against experimental-wise error or type 1 error. And here's what they did in this study. This is a study these guys did a while ago. They did a meta-analysis, and they looked at studies with sample sizes of 10, 30, or 50 subjects and rounded them off. So you see under sample size 10, 30, or 50. They looked at studies with 3 DVs, 6 DVs, or 9 DVs roughly. You see that? Number of variables means DVs. They looked at studies with different proportion of variance in common. In other words, how much intercorrelation was there among the DVs on the average. And what they're doing here is looking at, they put them in categories of around 10% in common, 30%, 50%, or 70% in common. How would you get percentage in common out of correlations? Squared Pearson's give you percentage of variance in common. So imagine you had the 3 DVs and you had correlations of 0.3, 0.4, and 0.5, and you would square those and take the average of those. That would be the proportion variance. So you can kind of roughly get that. Then the numbers in the body of the table are the actual probability levels they got out of running hundreds of Monte Carlo trials. And so what should those numbers be? Those numbers should be 0.05. And if everything's working as it's supposed to, the numbers in the top portion should all be 0.05. So you can see that in the condition of 3 DVs with 10 subjects per cell, first row far to the end, they got pretty close to 0.05, 0.077, which what the real actual probability levels were. They were supposed to be 0.05. But you look at some of the other ones that are much worse. Look at sample size of 50 subjects per group with only 10% of variance in common. The actual alpha level was, the found one was 0.324, almost 6 times higher than 0.05, or more than 6 times higher than 0.05. You get how that works? So this means that if you're doing a bunch of DVs, you are having a problem with type 1 error. In some cases, very serious problems, like that one I just gave you, where your conclusions are off by a factor of more than 6. In other cases, very minimally, like the 0.077 or 0.085, one's over the side. Those are probably negligible amounts of type 1 error. So if you happen to have a situation where you had quite a lot of correlation between your DVs, and you only had 3 DVs, and you had a small sample size, and you decided to run 3 ANOVAs, see what they're doing, they're running separate ANOVAs on each DV here. Maybe that was a piece of this. Get that? And they run separate ANOVAs of each DV, then they count up what are the actual probability levels they get from that. This is running on data that's not significant to start with. It's a bit complicated. We'll go through it again. They take a data set that is actually no significance in it at all. It's random numbers. In this case, in the top portion here, what they do is they rig the numbers to be in different correlations with each other. From, a couple percent to 70% in common. They then ran all of those separate DVs as separate ANOVAs, and then they averaged out what the actual P levels were found for those. And instead of finding only 5% of the cases they got significant, which they would like to get, in some cases they got 32% of the variables were actually significant. Which is a big difference. So you can see that it isn't really okay to run 1 million DVs and just pretend like the 0.05 level exists. You have to do something to do it. So one of the strategies is, well, what if you ran a MANOVA first? Now remember, this is a MANOVA on random data, so you're not going to get too many of them significant, right? On the bottom half, they first did multivariate tests, which test all of the DVs at once. And then they looked at the alpha levels that they got as a result. And you can see actually it's slightly overcorrected because all of those are below 0.05. There's nothing above 0.05, and some of them are actually quite a bit below 0.05 on the bottom. So it's a little tricky because, remember, in this situation at the bottom, not too many of those are going to come out. It's just a rare case when the MANOVA is going to be significant. And in those particular cases, then all of the univariates would be unlikely to be significant. But it does offer the rationale for saying, okay, I'm going to run the MANOVA. You have to have some confidence that your DVs are all going to pick up on something. If I get a significant MANOVA, I'll go ahead and use my univariate ANOVAs and interpret them separately, and I won't make any correction for type 1 error. Justifiably saying that I'm okay because I'm protected. The risk of that is that your MANOVA, the overall MANOVA is not significant, and then you have to stop. So let's see, you have 5 measures, like in this case we have here, and homonegativity was your main one. And that came out really nice and significant, and the other ones were not significant at all. And in this strategy, you're done. You can't even interpret that one, or you have to interpret it with great caution because it could just be a type 1 error. Now the other alternative, which we kind of like, is to use the top half of the table to do a modified uniformity under the circumstances that you're in. So a student came in to see me with a study where they were comparing yoga to CBT for symptoms of fibromyalgia. And fibromyalgia has a number of different scales that are used to measure the symptoms. The fibromyalgia impact assessment, the fibromyalgia impact questionnaire, the Ames anxiety scale. So she had 5 different measures that measure different aspects of fibromyalgia. We didn't think we should put them all together because they don't measure the same thing. We wanted to look at them separately. If we were to use a straight bone Ferroni, how would we do that? How would we test each of those 5 ANOVAs with a straight bone Ferroni? Remember the first semester? Ferroni at the San Francisco treat. Remember that one? Close. So yeah, number of variables. What's divided by number of variables? 0.05, right? Let's just take 0.05. Bonferroni was an Italian statistician, he's a sociologist. He said if you have 30 correlations that you're looking at, take 0.05 divide by 5. It's straight up Bonferroni. So in her case, she would have had to take 0.05 divided by 5. Everything would have to be significant at 0.01, which would be pretty strict. But if you look at this one, let's pretend she had 10 subjects per group, and she had, we'll go to 6 DVs because she had 5, it's close. And her proportion variance in common was a 0.3. So her rate for hers was 0.19, that should be 0.5. That's about 3 times more than 0.05, right? Once we look off, we say somewhere between 3 and 4 times too high. So we could then divide 0.05 by 3 instead of by 5. Makes sense to you? And that gives you a better chance of getting significance. So this is, the trouble is that, aside from Omar, Connie, and myself, none of the faculty understand this. So if you go into your chair and try to explain it, you have to really be sure you can explain it to them and show them the chart and make it work, so, or else have us come in and help explain it. But it is, in Elisa's case, it actually made a difference in one of the variables, which would not have been significant without it, and with it, it was significant. So we actually could say with some confidence that the yoga had a slightly superior effect than one of the variables. So, what do I need to go over again? That's complicated.
Then you lost me after .03, and then
Okay. Let's look. So, remember the straight bone for only would be 0.05. That's for works. 5 divided by 5 if we had 5 dBs, right? And that would be 0.01 would be our new critical value. Okay, on this one, looking at the particular one, she came out with a 0.19, right? So 0.19 is like, that's the second row, second over. See, 0.190? What do you find that?
oh, there. Okay, I was looking at the bottom.
Yeah, no, you don't do the bottom one for this one. So see, the bottom one is just to show you that MANOVA works. So 0.19 divided by 0.05 is somewhere about 3.5 or something. 6, I think we brought it down to 3. So if we did that, that means that the bone for only is a bit too strict, 0.01. Divided by 5, but what if we divide this by 3? So now we do 0.05 by roughly 3, actually 3 something, and that equals
0.01.
So we gained a little bit because now we could round that to a 0.02. So our new critical value would not be 0.01, it would be 0.02 in this case.
How are you jumping from the, I see where you have 0.19 and then you change the denominator to 3 because you're making it less variables? Is that
No, because it's 3 times, I'm roughly saying 0.19 is about 3 times higher than 0.05. It's actually, what is 0.19 divided by 0.05? Let's do it back. So now here we do 0.05 divided by 3.8. And that would be see how it works. So it's sometimes a good strategy. For instance, if you were going to do, if you happen to have the case of the 10 per group with a 0.7 in common, the last one, the 0.077, you probably don't need to make any correction. This is a tiny amount of experimental error. There you could get by with almost 0.05, so maybe 0.04, and you'd be safe in doing that. And as long as you can justify it, both in publications and for your committees, that's a perfectly legitimate way of doing it. So there's a kind of 2 ways to go. The other way to go is if you have a lot of confidence in all of your DVs, you can do the MANOVA, and you win the live or die by the overall multivariate significance. Otherwise, you can try to do this one. No, it's the 0.05 divided by the number of variables. Well, I was rounding that. In her case, it was 5. Sorry, I just made where it's close enough. So in this particular study, she had 5 dBs. So I just rounded to to use the 6 one. You're right, though. There's not any more values in the studies than this. They didn't do every possible one. So you have to just kind of guess from this one where you'll be. But you're going to be pretty close to, if you have some doubt, you can change that to 0.01 or something. So in some cases it's quite advantageous, in others it's not. In the cases, the worst case, the 0.324, is just about the same as a straight bone flow.
So I think it's 0.2 column over.
That's how much variance in common she had. I'm just making it up.
Oh, okay.
Yeah, you find out from your DVs. So we got all the correlations, we squared them, we got the average of them, and they were somewhere between. I just made it up. I don't know what was actually. So if they're more correlated, you get a little bit of a break. If they're less correlated, it doesn't really work very well. Okay. Oops, sorry. I'll come back to that slide in a second. So what does the output look like? Well, what MANOVA gives you is some new statistics that we're not used to, although a little bit used to them from discriminant. These are the multivariate test statistics. And almost all the programs give you 4 of them. Wilks lambda is the most common one. The lower the value of the Wilks lambda, the more significant the finding is. These are statistics that represent the latent variable of all of the DVs. Now, if you have a bunch of DVs, you might have more than one latent variable, right? Just like with discriminant. Remember, in discriminant analysis, if you have a bunch of statistics in there that you can get, the latent roots could be 1, 2, or 3, or 4, however many you have. So you may have more than one latent variable, and these top 3 all test all of the latent variables. The first 2 and the last one test all of the latent variables. We'll talk about the other one in a second. Wilks lambda is kind of it's sort of equivalent to 1 minus the Wilks lambda is something like an R squared. So if you have a Wilks lambda of 0.3, it would be kind of like an R squared of 0.7. And so it's a common test. The other 2 are similar, the Palais-Bartlett's trace and the Hotelling-Lawling's trace. Some have explained variance on discriminant variates, related variables. This one is the most robust to violations of assumptions that we're talking about. So people are drawn to it because we often violate assumptions, and you kind of somewhat justify getting around that by using that particular test. Hotelling-Lawling is very similar to the Palais-Bartlett's trace. The one that's quite unique is the Roy's greatest characteristic root. It's very similar to the other one, except it only tests the first latent variable. If there's more than one, it only still tests just the first one. And that's quite useful because quite often you only really care about one latent variable from your DVs. You're kind of hoping for one construct among your DVs that are going to give you the answers you want. And so the other ones might not be very meaningful to you. We'll see later when we use discriminant analysis how to interpret the latent variables. So typically, since it's only on the first one, it's more powerful, but it is also more sensitive to violations of assumptions. So you'll see in a minute when we look at some output that the output produces these 4 multivariate statistics. You may have seen them before because when we did repeated measures of MANOVA on SPSS, it automatically does the multivariate first, even though we never interpreted those last semester. Another multivariate test, I don't think the book talks about this one unfortunately, is called the Roy-Bargman step-down in MANOVA. It's kind of a mixture of a stepwise regression and MANOVA. And it can be a very conservative test if you're not in an area that you know much about. Does control for type 1 error pretty well. The step-down test performs the univariate ANOVA on the first DV. It finds the best DV, does that ANOVA first, then it adds the second one, and it keeps on going until nothing more is significant. So you can kind of build the model experimentally, which is not very good for theory, but sometimes when you don't know what you're doing, you're just starting off, that's actually not a bad way of proceeding. The order is critical, and if you determine the order yourself, then it could be theoretical. You could use theoretical. If you let the computer determine them, then it's like a stepwise regression. It's easily abused. So you get to load in the variables, and then you say, oh yeah, that's what I thought all along. It's calling the winner of the horse race after it's over. That's not very powerful. And then, as you'll see, we use discriminant analysis to actually determine the nature of the variance. What we're going to look at from we did is the one that's like factor loadings, the coefficients that look like factor loadings, because they kind of help us interpret what the variance mean, just like they do in the discriminant. And you need to decide if you want to only look at the first one. So now let's take a look at the output I gave you. We'll actually see how this works. Oh wait, I skipped assumptions. Sure, you would love to skip assumptions, actually.
Yes.
Sorry. All right, so here are the assumptions, the grand finale of the 2 semesters. First ones are very familiar. Independence of observation, which is really important in MANOVA, as in most things. So you do not want to violate independence of observation. Homogeneity of variance, which is just the univariate homogeneity of variance. So you just look at the Levine's tests or an SPSS to make sure you haven't violated that. Now you've got univariate normality, so you can look at each DV and assess it for normality in the usual way with the Smolov test, or with the dividing the skewness and kurtosis by standard errors. Remember from the project first semester, everybody obsessed over those. So you can assess univariate normality. You can assess linearity between the DVs. So the assumption is that DVs are linearly related, not curvilinear related. Usually you can meet that one, but that's the problem if you can. Now you have some new ones, one called multivariate normality. In the slides, I think I gave you, I forgot to put it in my slide, but if you look at, look on the little drawing like this. This is the one that gives you an idea of what bivariate normality would look like. Since I can't draw it, which I might put a thing in here. And then the bottom one is some variation from it. So when you're assuming 2 variables are bivariately normal, you're experiencing this kind of nice even bump among the 2. And then here you can see that that's kind of a wedge, so it's not quite as normal. Now we can expand that to beyond 2 dimensions to 3, 4, 5 dimensions. There's a kind of concept of multivariate normality, which is that all of the DVs somehow, if you could do it, would create nice even bumps in some n space. Of course, we can't ever see that. We can't go beyond the 3 dimensions, so you have to go to Comic-Con to see that or something. So the way we do that is we have some statistics that look for multivariate outliers. Remember we talked about them earlier in the year, Mahalanobis distance score. So the Mahalanobis score is a score that looks at each individual case and gives it a score that represents multivariate distance from some theoretical normal case. So the only thing we can really do for these is look for multivariate outliers. So you could have a case of somebody who's not a univariate outlier, not a bivariate outlier, but is a multivariate outlier because they're at the extreme of every single measure, and that's so unusual with the extreme of all of them that they would then be an outlier. You kind of imagine that in the 3 dimensions. So those people come out with big Mahalanobis above 20. And you can look for those and say, well, look at this particular person, and then it may turn out that there's a mistake in the scoring, or that they're weird, or they went to Comic-Con or something. So we do try to look at multivariate normality. It's kind of an art more than a science when we do that. And it turns out that, oh, let me finish this. So the other one is homogeneity of variance covariance matrices. That's the same one as we saw in the discriminant analysis. That assumption, remember, is imagine that for each of our this is not my technology data, that's for sure. Let's say we had 3 IVs. IV1, 2, and let's say we have 5 DVs. So we could have a matrix of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, 1 versus 1 is just the variance. 1 versus 2 is a correlation. 1, 2. 1 versus 3 is a correlation. R1, 3, etc. All of which we have variances on the diagonal, and correlations or covariances on the off diagonal. Covariances are just unstandardized correlations. So they're big numbers that don't look like correlation coefficients, they just have a standardized one. So we have, so this is called a variance-covariance matrix. And so in MANOVA, as a discriminant analysis, we have 1 for each IV. Discriminant, we just had 2 of them because we're just looking at 2 choices. So the assumption is that these matrices are no more different than you'd expect by chance of it. So that means they could differ in a lot of different ways. They could differ because the variances differ, which would be a homogeneity variance violation. But you can spot those by looking at Levine's tests. So you look into the Levine's test, you'll have 1 for each DV. You could say, no, I haven't violated any homogeneity, so we know that if there's a violation here, it's not coming from that. It could come from some of the correlations here being very different from correlations here than here. And then you're going to have to look at the correlations to see where those might be. Because if, in fact, you have a random control trial, and the correlation between the fibromyalgia impact scale and depression is way bigger for the yoga than it is for the CBT, that would make you wonder what's going on in that data, right? Why would it be that people in one group are correlated different than people in another group? Could happen. And again, when there's static group differences, when you're looking at bulimics, anorexics, blah, 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 those are likely to be different correlations. They're very different groups. So this is a tough assumption, but there are some ways around it that we'll see.
Is the matrix provided on the output?
You can get the matrix in the output. So you'll see in the output, we ask for the SSCP this time now. We never have asked for it before in our check mark. It's the sum of squares and cross products. So we ask for those, and we ask for the standardized one. The standardized ones actually give you correlation coefficients in this matrix. The variances are given in the diagonal, but you can also see those in the Levine's test. So you can do it. Now, one of the problems is this assumption is also sensitive to violations of normality. And just like in discriminant analysis, we test that assumption with the Boxes-M test. So the Boxes-M, the good news about the Boxes-M is if it's not significant, you're in pretty good shape on assumptions. Unless you violated independence of observation, which you should really never do, you probably don't have to worry about your assumptions anymore. However, the bad news is if it's...
You said it's sensitive but not specific.
Exactly. It's very sensitive but not specific. So, but if you want it not significant, yeah. But if it is significant, it could mean many things. It could mean a violation of normality. It could mean a violation of homogeneity. It could mean a violation of regressions, regression of correlations. And that would be, and you got to go snooping around to see how serious it is. So later we're going to do MANOVA, where we now add the final assumptions from the whole year, which is linearity between CVs and DVs, and homogeneity and slope between CVs and DVs. So now when you do MANOVAs, which should convince you never to do them, you have every assumption we've ever had for the whole semester. However, there is kind of some good news. This is a little hard to see on the slide, but you have a full-blown version of it on the next page here. So our buddy Stevens, who's a kind of big MANOVA expert, kind of looked at all the literature and came up with a kind of a decision tree for situations about assumptions and ANOVAs. So he says, first assess independence of observation, and we want to always make that true. So really, if you have some reason that you don't have independence of observation, you need to go get a consultant somewhere because you got to mess it up. So that won't happen to us very often unless we're doing some econometrics gets this problem. There's some areas that have these problems. But one area we might see it in, and what we probably wouldn't do ANOVAs, would be in diary data. Diary data is pretty practical for clinical psychology PhD students to do because you can kind of do measures on people every day with reasonably small samples and get giant data sets, right? So if you had 21 people doing their daily cortisol and their daily stress, you end up with 20 people, you end up with 400 observations per person. So you get quite a lot of power in observing the relationships. But those are usually going to be regression studies. And it's not so hard to deal with independence of observation and regression. We haven't gone over it, but if it ever happens to you, I have a whole packet I can give you on how to do that. You subtract out the intercorrelations. It's not so bad. We do it all the time in studies we do. Because I'm very interested in physiology and stress, so we often have studies where we're looking at things over many observations and we want to see some physiological measure every day, some stress measure every day, some mood measure every day. So now you get these things. And those are not going to be independent, right? You get a bad couple of days and a good couple of days, and on it goes like that. But for the most part, if you're doing MANOVA, you're probably not going to have that problem. So let's just assume that we're going to be smart and not violate that. So if the assumption, assess assumption, yes, assess multivariate normality. So the way we do that is by looking at all kinds of normality, univariate, bivariate, and multivariate with all MANOVAs. So you look for normality for all your measures. Just because some of them are not normal doesn't mean anything, but you can still snoop through them. The ones you want to really watch out for in practical situations are skewed measures that look like this. Right, there's a 0 point here. There's nobody to the left of 0 because 0 is the lowest score on the scale. And most people score 0, 1, or 2. That's something you do not want to have happen. You see some tearful reactions in my office when people use the Beck Depression Inventory for normal mood. And this is exactly what you get if you do that. Most people in the Beck are 0, 1, 2, 3, 4. And then a few people are depressed up in the 16, 18, 20, 30 mark. So if you're looking to assess something effect on mood, you do not want to use the Beck because it'll give you a completely non-usable distribution. So make sure the measures you use, at least, they may be skewed, but at least they're skewed like that, then you can deal with that. Truncated floor effect like that, then you've got troubles. So let's say even if you have some skewed variables, they're not terrible. You've assessed it. You assess that. You look for your MANOVA scores. You can maybe find 1 or 2 people. If it's a big sample, you can either Winsorize those people. We talked about Winsorizing. Move them down to the highest level. It sounds like a dry cleaning term. Take it to dry cleaning. Or you can throw them out if you're pretty sure that they're really bad. Then you look at the group size. It says if it's greater than 20, just kind of look at graphical tests for the normality. If it's less than 20, check for univariate normality with all the kinds of things with Kolmogorov, Smirnov, the other tests. Let's say that you do have multivariate normality, no. It says no, then you have to kind of do some other things. Let's go to the yes first. So it says yes, we don't think we have too big a problem with them. Check for homogeneity of covariance matrices, that's the boxes M. Make sure you don't have any terrible violations there. Is the assumption tenable? You're good to go. Let's say it's not tenable, no. Are the group sizes approximately equal? Something to plan ahead on. If there's no more than 1.5 to 1 ratio between the two, the lowest to the highest group size, according to Stevens, which you can quote, it's okay to go ahead if there's decent group sizes. In large group sizes, no problem, since the power is adequate and type 1 error only slightly affected. If they're not equal, find the variance stabilizing transformations and approximate variables, or adjust largest alpha level accordingly. So now you're going to have to get into some careful alpha adjustments if you're going to, because the violation of that assumption typically produces type 1 error. So you might just have to use a stricter alpha level. You probably wouldn't have to give up on the process. This one is try to find normalizing transformations. We often find that if you get a skewed distribution, you go into a logarithmic transformation, you can get it to look better. You do it both with transformed data and not transformed data. There's no difference in your conclusions. Don't use the transformed data because it's a crazy measure. It's a logarithm of the Beck. Nobody knows what that means to have a logarithm of Beck unless the scale is already logarithmic. So kind of good with that. So it's actually not as dire as you would think, as long as you have reasonably decent sizes and they're about the same size. Okay, now we can look at the data I put out here for you. So I might put page 1 first today. Okay. So this study was, it's actually kind of a rigged up data, a very simple one. It's just the first page of it. If you look at the second page, you can see what the variables are. The second page here. Page 2. Page the second page. Page 3, I skipped page 1 because it didn't have anything we cared about. I'll come back to page 2 in a second. We'll skip a little means for a second. So, just so you can see the names of the variables on bottom page 3. So what we're looking at are 3 kinds of therapy for OCD. CBT, behavior therapy, and a control group. We're not looking at pre-post scores here, we're just looking at improvement scores. But instead of measuring just one thing or another, they measure number of obsessive related behaviors and number of obsessive related thoughts. For OCD, it would be important to know not just the behaviors, but also the thoughts. So that would make a lot of sense to put those together into one MANOVA. In this case, probably this does make a lot of sense to use them as a MANOVA because we really want to capture both the thinking and the behavior. Somebody might be able to stop their obsessive behaviors, but they're still completely plagued by obsessive thoughts. Or someone might be able to stop their obsessive thoughts, but they still have to check the house 30 times before they leave it, which interferes with their life. So we want to really see both of those things going on. So that's what this study is about. It's a fairly simple one. So let's look back on page 2 now. And the first thing you do is see the box is M. And the box is M. Hallelujah, it's not significant. So at least to this point, we're in pretty good shape in terms of assumptions. The next box, it gives you the multivariate test. We never care about intercept. This means if the baselines are different than 0. We don't mean anything in this case, but we do care about group. And you can see the 4 different multivariate tests, the Glaze, Wilks, Hotelling, and Roy's. It gives you the values, which are kind of meaningless except for the Wilks lambda value, the 0.699. That one you can kind of interpret because 1 minus that value is like an R squared. The other ones need to be transformed into F's. They're all transformed into F's. The computer does that. It's already squared, so it's just be like 30, about approximately 30% of variance of half. 1 minus that. 1 minus 0.6. So the F statistics have complicated sets of degrees of freedom because they're multivariate statistics, but You don't have to care about those because the significance is what you care about. So if we look at the statistics, we can see that all of them are significant except Hotelling's trace, which is a little bit off, 0.051. But they're all pretty close. But notice the Roy's largest root is the most significant. And that will usually be the case because it's only testing the first root, the first variant. And I think in our case, that's probably the most important one. We probably don't care about them. You'll see in a second what they are. And I think that's going to turn out to be okay. Finding here, we would probably interpret the multivariate statistic as the way that works.
When you say testing the first one,
Well, it's going to create two latent variables. The computer creates two latent variables. The other tests test all of the latent variables, however many there are. Roy's only tests the best one, the first best one.
and that's between obsessive thoughts or obsessive.
No, it's a combination of the DV, yeah, between thoughts and behavior in some combination. In this case, it's pretty simple because it's two,
Right.
but it might be one higher. And then the eta squared works just like all of our eta squares. So you can see there's a pretty good effect size for Roy's. And then the rest of it we don't care about so much. Okay, and then the next page we can see is Levine's test. So both of those are testing homogeneity variance for each DV, and neither of them is significant. So that's pretty good. If they were very significant, probably the boxes M would be significant too. So one of the things you can do if you get a boxes M significant is check your Levines right away. If you got a real bad violation of homogeneity of variance, that might be a problem. Why would there be so much more variance in one of the others? One group for one of the three different treatment groups. So we're good on that. Then this is the test of between subject effects. There's no within subjects in this case. So these are the univariate MANOVAs. Again, we don't care about corrected model or intercept. We look at group and error. Those are our usual kinds of Fs that we're used to. And you can see the two Fs. Now in this case, you can kind of see 2.771 and 2.154. Those are kind of low on our group differences, right? And if you flip over to the next page, you can see that actually neither of those is significant at 0.05. Both have decent eta squares, but fairly small sample size, so we just have a power problem. However, in this case, we got significance at the multivariate level, but not the univariate level. So in this case, we made up to kind of say, if we look at both thoughts and behavior, it looks like our treatments differ from one another. But if we look at them separately, it looks like we conclude there is no difference between the three different treatments. So then if you go and look at the sum squares and cross product matrix on page 6, I believe it was the bottom, it gives you those numbers. Those numbers are hard to interpret by themselves. They give you error rates as well as the actual hypothesized relation at the top of page 6. So those numbers are cross-product sums that they by themselves don't mean so much. You divide them by their error rates and look at the differences. Usually, though, most of us just look down at the correlations that I circled just to see what's correlated with what. In our case, only two DVs, so we got a 0.165 correlation between thoughts and behavior. It's not a very big one, but this sample size is probably not a significant one, but it seemed to work well enough to give us.
Wait, so you divided by what?
Well, if you the correlations are just calculated for you. If you go to the top one and you divide the 616.553 divided by 51, you come up with a number that kind of represents the kind of a standardization of the cross product. But unless you really understand the matrix algebra, that's not going to help you very much. So really, you just want to do this in order to be able to get the correlations. The covariances are the unstandardized versions of the correlations, and they're also not reducible by themselves. So we want to look at them in terms of correlation coefficients. Now, if you had a violation of the boxes M, didn't do that here for you, but we could. You would go in and do a split file and look at the correlations within each level of the IP. Because we want to see where those correlations differ from one another.
The last one, what is this down here?
Those are correlations between obsessive thoughts and behaviors. Just straight Pearson correlations.
We go back just like we divide the group by the where and what we get from it.
Well, you get a standardized version of the cross product matrix that kind of gives you something similar. But really, I don't think very many people use that. If you're not really familiar with matrix algebra, it's not very useful. So to get to my last point, if you've got a violation of the boxes M, and the homogeneity was good, now you're probably, your sources of assumption violation are either going to be normality, which hopefully you've checked already, or it's going to be correlations between these groups that differ a lot. Right? And how are you going to know that? You're going to only know that if you go in and do the sum of squares of cross products by each group separately.
So it's too little correlation between the groups?
Different. It doesn't matter, yeah. So too little means MANOVA probably isn't useful. Too much means MANOVA also is not useful. But the difference between the three levels of the IV is what we really would care about. So let's say that thoughts and behavior were correlated 0.7 in CBT and 0.2 for behavior therapy and 0.5 for controls. That's a problem, right? Why would those two things be different in each of those groups? It could be good. So that you could probably spot where that's going to be. And that might be a reason to not use MANOVA, if that's the case. The next step would be all the things we do with MANOVA now. We would do plan comparisons or post hoc contrasts. And we're going to probably save that for next week. So more advanced. However, if you look at the graphs of the two BVs, you can kind of see where our multivariate significance probably came from. These are the number of obsessive related behaviors. The behavior therapy did really well in those. CBT did not do very well. They did the same as the controls. We go to obsession related thoughts. CBT did really well. Behavior therapy did not do so well. About the same as the control. So these are kind of made up data. So the answer is that you do both. The good ones, you do both either ACT or CBT and behavior therapy for OCD, and you get good results with them. And if you're able to do those together, you don't just do one or the other. So if you just control for constrained behaviors, you don't get rid of thoughts. If you just do the thoughts, you don't know how to get rid of behaviors. You have to get people to constrain their behaviors and work on their thoughts at the same time with CBT or ACT. And that actually works really well for us. But to find that out, we would probably have to do some specific comparisons, like we always did last semester. And here you might want to do them with univariate ANOVAs. So you can understand them better by looking at the two ANOVAs. Even though those overall ANOVAs weren't significant, if you did a comparison between just CBT and behavior therapy, you're going to probably get it from this one. That's probably significant. And that's probably significant. The overall ANOVA, because of the two cohorts here, probably significant. All right. Now the discriminant analysis will help us kind of figure out how the MANOVA worked. It's pretty simple here because there's only two DVs. So what we did, here's the group statistics. So if we look, the main thing we really care about in the discriminant analysis when we're following a MANOVA, I think I circled it over on page 3. Usually people pay attention to really only one thing, mostly the structure matrix is mainly what we want. Or you can use the beta weights too. So the standardized canonical discriminant function coefficients are like beta weights in regression. And they kind of tell you the standardized weighting for each variable, for each function. But the one we really kind of want is the structure matrix. And it really makes total sense here, right? Because the first variant gave us a real positive weight for behaviors and a real negative weight for thoughts. So it's working in those two things together. That's why the Roy's was so significant, because it worked those both things together. The second one gave us pretty high ratings on both of them. So it's a pretty hard one to name. Whatever that is, it's like whatever in common between the two. Probably not a very useful variant for us. You with me there? The first one, 0.711, and the minus 0.576. Think of those as factor locus, right? So what's the name of that factor? OCD is the name of that factor, right? It's thoughts and behaviors that are working with each other in somewhat independent and somewhat correlated ways. It's exactly what we wanted from that. So if you can kind of name that factor and make a meaningful latent variable out of it, that's a really useful thing. The second one, I don't know what you would name it, they're both high. So it's another aspect of OCD, but it's not the one that we think is really working in this particular discriminant. Because what really separates those groups is high thoughts, low behavior, and behavior with thoughts in some graph. But it's tricky sometimes to figure out what those mean. But the only way you're going to know is by looking at the discriminant analysis. So usually we do them mostly just to look at. Now notice in this case we used 3 groups as the outcomes, not like we did last time in discriminant, which is two groups. You can use any number of groups in discriminant. So here we use CBT, behavior therapy, and control as the outcome, putting in 1, 2, 3. And then this is what you get from it. And that's why you've got 2 functions here. Usually we don't care much about the rest of the discriminant because it would just tell us how to classify people into groups, but we don't care about classifying them into therapy groups. That would be a useful thing. So use the discriminant just as a way of interpreting the latent variables within here. It's a pretty common practice.
You said you can't really name factor 2.
Yeah, well, I don't know what I would call it. It's sort of equally high in both thoughts and feeling behavior. So some part of that is working there too.
Does it matter that factor 1 and factor 2 are similarly high on obsessive related behaviors?
Well, no, they're separate. It's like any loading. It's picking up separate things. Since we already knew that the first latent variable is only significant, then we probably won't interpret the second one anyway. The second one, if we use Roy's, we've got nice significance. If we use the other tests, they weren't significant. So that means that second one probably is not meaningful.
So why is it that a factor of negative 5.7
Because the best way to separate people would be high on thoughts, low in behavior, low in behavior, some combination of those two was the best way they could separate by groups. Really, in this case, it's purely coming from the way the graphs work. Where we got one condition produce one thing and another condition produced another. So it gave us a kind of a nice combination of the two. You'd like to see something happen. It would be nice if we had another group that combined CBT and behavior, and then we would see a completely different pattern. Probably that group would be lower than the other ones. And that might give us a completely different weight. So it's trying to give you some way of helping to interpret what that first factor is, the first thing. It's not always easy, but usually you can figure out something from it. Now, the most common thing you would hope for is that you're doing a study and you're using 5 measures that you think all tap into some aspects of the same construct. Construct of depression is a vulnerability or something. So you don't think there's any one measure that captures all aspects of it, but you think together they really capture the whole. Then you would want the latent variable to be just both very high. Both weights would be very high, or 5 weights would be really high. Just like in factors. And you say, well, that really is the construct I'm looking for. I want to stick with that one, and that's what it might lead somebody to actually put together another measure that puts all those things together into one measure. So sometimes you need to do it. For most of us, that doesn't happen too often. Most times the dissertations are ending up with just throwing a bunch of measures and problems you want to measure, and they don't necessarily go together in the construct, so we're just looking at a bunch of these. So in those cases, we don't let people do MANOVAs very often. People get a very MANOVA is incorrect for technical. My students do a lot of treatment outcome studies with biofeedback or ACT, line, wisdom together, with yoga. So in those kinds of cases, we're measuring some disease, some problem, irritable bowel syndrome symptoms, or fibromyalgia symptoms, or headache symptoms. Well, there's no one headache scale that's really perfect, so we end up with some different aspects of headache. We look at them separately. We also wind up on depression, we wind up on anxiety. Those don't necessarily fit into the headache one. So you often want to use separate therapies. Okay, let's take a break and we'll come back and look at a two-way version of this. 2 DVs, emotion and worry. Okay, so there's the data laid out in the usual way. You just put in each DV separately. And then do analyze, general linear model, multivariate. Dependent variables, you just put them in together. And the independent variables go here as usual. Your options, you choose, get the means for the interaction. Do the 3 here. This time we're going to do these 2 at the bottom as well. Sum of squares, cross products, and homogeneity tests. Usual suspects plus these 2. Got it? And we want to do plots, so we would want to see treatment, horizontal, gender separate lines. And that's probably all we need to do right here. And if I did it right, you should have the results in front of you. It's starting on 2-way MANOVA, no repeated measures. Okay, so we're looking at medication, psychotherapy, or a placebo. 34 and 32, 34 per group. 50 males, 50 females. First gives you the means, standard deviations. You can see we didn't get a great distribution of gender by the different conditions. We had 32 females and only 8 in the medication group. That's a bit of a problem. Here's the boxes M, so good news again, not significant. The Bartlett's test of sphericity just tells you whether there's enough correlation among the DVs to be significant. It usually is quite significant. Should have one in front of you. Next is the multivariate tests. And here we've got main effects for gender and for treatment. It works just like ANOVA. So we look at the significance levels. Now in this case, every single indicator is significant for both gender and treatment. Gender has a big effect size. And the interaction is significant for all of those, but especially for Roy's root, the first variant. We're going to want to try and pay attention to that later. The effect sizes for the interaction aren't as big, but what do we do when we get an interaction and main effects both significant? What do we do when we get both the interaction and the main effect significant?
We have to stay with the interaction.
You look at it.
Interaction. We don't care about the main effects right now. We're going to look at the interaction. We're going to want to see where that's coming from. So let's move on. Homogeneity of variance not violated. So since there's no repeated measures, the only output univariate is between subjects' effects. So it does it for each of the dVs. And you can see we did get a little bit of a problem here. For the worry dV, there was no gender effect, only for motion. And again, there was no interaction among among worry. For the worry dV, there was not a significant interaction. It was a big one for the emotion. So the multivariate is picking up mostly on the emotion variable, although there's some big main effects for the others. So when we're going to look at these, we're going to have to decide how we want to interpret that. Do we want to look at it with both emotion and worry together, or do we want to separate them out? In which case, we would say, okay, no interaction between gender and treatment, but there is a main effect for both of them, for both males and females. The interaction is all going to be in the emotion dV. It is for males reacted differentially from females for the emotion dV and not for the worry dV. We'll see it in the graph in a second. Okay, with me?
So you would still say that there's an interaction, but it's only based on the emotion differences?
Exactly. Yeah, and so now whether we want to put those together in one combined variable, we might, and then we can interpret the multivariate output, or whether we want to separate them out, that's a decision you have to make. Okay. Here's the sum of squared correlation. Here we can see there's a pretty hefty correlation, 0.627, between emotion and worry. But remember, even a 627 is still only about 39 or 40% of the variance. Most of the variance is still not in common. Okay, with me? Gives us the means. And let's look at the graphs. So these are for the emotion dV. You can see the males were higher, and especially looks like in therapy and placebo were higher than the meds for the males. I don't know when males are ever higher in emotion than females, but probably made up data. They might be, but they never admit it, right? And then for the worry, you can see that they started off on the meds, both groups were lower in the meds. Looks like therapy maybe differentially affected males and females, but probably not in the placebo. That interaction seems to be coming from there. And the fact that we don't really, I guess we get it there too, but this is also big, so kind of a confusing picture if we wanted to do that together. Okay, so now there's a lot of ways to go if we want to go. We could say, heck with it, I'm not going to try and do the MANOVA, I'm going to just do two ANOVAs, one for worry, one for emotion. Know how to do those. I can do simple effects on those. I can do simple comparisons on those. All the things we did last semester. And probably I would, if I want to be conservative, I could just use a 0.025 alpha. Or I could use that thing we talked about earlier and see what the real inflation is. Maybe I don't have to go quite to 0.025. And just use the univariates and don't even look at the MANOVA. or if I think that MANOVA maybe gave me something that I wouldn't see otherwise, I might do it. So let's do the discriminant analysis, see if we can get anything out of that. So we'll go to classify discriminant. The grouping variable is independents are going to be emotion and worry. Now we can only do one of these at a time for this one. So we have a choice. We could put them into 6 different groups. I could reconstitute those into 6 different groups if I wanted to. Because if I do it just by treatment, I'll get the discriminant just on treatment, and then I can do it just on gender. But that doesn't really capture both of them. So what I could do, I do have 6 different groups of people here. So I could recode these as 6 different groups and use that as the independent variable coded from 1 to 6. That'll get me a bunch of variates, a bunch of discriminant functions, 5 of them probably, or 6 of them. So here's what I'll show you how to do that. I'm not sure I'd want to do it in this case, but let's see. So we can either do it with transform, recode. That's a good one to learn to do. Let me show you that one. So transform, recode into different variables. What I'm going to do is the input variable is going to be gender and treatment. And then I click old and new variables. And if the value is going to be, I have to remember how we coded those. Can you see in the data? I think he did 1, 2, 3. Let me go back for a second and look at the data. I can't remember how it was coded, but I can't see. Okay, so 1, 2, 3, and 0, 1. You need to know how you code 1, 2, 3, and 0, 1. So what I could do, one easy way to do it is just go ahead and put down all the combinations of the groups. So all the 0, 1s get a 1. So for all the 0, 1s. Oh, sorry, wrong way. 1, 0s get a 1. So 1, 0, 1, 0. 1, 0, 1, 0, Did I miss one? 0. Did I miss one? I got it? 0. Put them in a funny order here so it makes it harder. Okay, then maybe I won't bother doing all these. So 1, 1s, we could make a 2. All the 1, 1s are 2. I did. Oh, sorry.
Another 1, 0.
I missed one. Did I miss one? A 1, 0, that's a 1. So I'm looking for 1, 1s. You can actually get the computer to do this for you, but this way you can see how I'm doing it. Oh, sorry, 2. I did this one wrong. Okay, 1, 1, 1, 1. A lot more 2s you can see than the other ones. I'll just do one more so we can actually do the discriminant, and then we'll worry about it later. I skipped the 1-1? Yes, I did. Okay, and then finally we'll do 2 1s as 3s. I won't do them all, but 2 1s as 3.
There's some 3 there.
Yeah.
Oops, sorry. 2 1 3, 2 1 3, 2 1 3. Oh, wait a minute. I won't bother doing them all. So then we would do the discriminant. We would put the DVs in here. They call them IVs in this one. Whoops, wrong. Worry, emotion. There we go. And then the grouping variable, whoops, is going to be this new variable, and it's going to go from 1 to 3. No, I'm going to make it into one variable. I'm not doing them all because I don't want to take the time. And then we just, do we need any of these? Probably not. So that would give us the variant canonical stuff. Only one function in this case. Oops, did something wrong. Did I not put a worry in there? Anyway, you see the idea. You would get it. Spend too much time on it. Or you can get the computer to do that for you. Or you could do it one at a time by treatment and put them in separately if you wanted to kind of determine where that is coming from. If you go to univariate, then it's all everything we did last semester. Multivariate, we would try to use this way. If you want to do plan comparisons with the multivariates, you have to actually reconstitute the coding with effect coding to say the combining groups 1 and 2, right? So you'd use a code like 2 for group 1 and 2. Group 1 and 2 would be 1, 1 minus 2. You do the coding like we did in plan comparisons last time. You actually have to code the variables that way. That way let's run a separate MANOVA on those particular ones. You can't do it the way we did it with mean differences next semester. If you go to the univariate, you can. Okay, so that's the basics of that without any repeated measures. And I think next time we'll go ahead and work on MANOVA and repeated measures in NOVA. I kind of do that with you. Let's make sure we have time to go over the project. So let's do that first. Give a little time to go back to this stuff. So here is the round.
Oh, sorry.
remember the rules are you get to work with one other person, find a partner, don't do it with threes don't work as well, and if you're really stuck, then come see us. You can work between classes if you want, and we just have to turn in two versions of it so we can grade them separately, and then we put them together after that. You need to include your computer output. If you want to save paper, do it 2 per page. You're double-sided and stuff like that. Don't forget to assess the assumptions. Most of the time we ask you to assess the data for outliers, normality. If you need to transform, tell us how you did it, show us what you did. Check this again. You guys think you're building version control. What was the data cleanup of this version? Just occurred to me I didn't change that. Might be the same. Yeah, it is. Yeah. So we just sent you the data set. It's called Katie's Stat Test 2011 data. You should have it in your emails. This is due in 2 weeks, right? Day of the final. If you want to get it in earlier, you can get it in. Oh yeah, so at least I better ask Connie, but if I don't know if she reads that. But for our guys, we can turn it in up till the Wednesday after the final, because we have that extra week. And we're not meeting that. There's a week put aside that we don't meet in. So if you want to turn it in after the final, though we recommend doing it, at least doing some of it before the final. It's good preparation for the finals. The data consists of 3 groups of subjects. True PTSD patients, real data. Patients that were asked to simulate being a PTSD patient, however they thought that would be, in controls. And we have a whole bunch of measures on them. So we have you'll see them on your data plan. No, not only in 6. Yeah, there's a whole bunch of things to do to kind of set it in, and the last one is really a write-up.
So it's not really like a big form of paper.
Well, the last one is like a paper. Let's see. All right, so the variables of the data we gave you, you have group data. Those are the 3 groups I mentioned. You have gender. You have ethnicity, which you can look at here and see how we coded ethnicity, race, age. There's a malingering 1 scale and a malingering 2 scale, and a malingering verbal 1, 2, 3, 4, 5, and 6 is the different subparts, and they're labeled here. So when you get your data, you can just expand that and it makes some sense. So malingering 1 is the total correct for trial 1. Trial 2 is given at 2 different times. Just reading the words on the Stroop. Everybody know what Stroop test is? And when the flash colors up and the words are in different things. Stroop, special kind of Stroop. Total time on the Stroop, total correct on the Stroop. You can see those are obvious. There's a PTSD score, the post-traumatic stress test that was used, so you get a single score on that one. There's a DAPS impairment scale. The DAPS is a commonly used trauma scale. Onset of trauma on the DAPS is another scale. Relative trauma exposure is another one. Negative bias is another scale. It's a suicidality scale. Dissociation composite score. Also put in a dissociation high-low scale. That's what I was going to show you. I need to show you how to do those. You don't need to do it because we did it for you, but you need to know how to recode data into median splits, high and low. To recode. You don't need to do it for this project, but you'll need to do it eventually. So remind me. Did I do it last semester?
You did it in one part.
Yeah. Just remind me next week and I'll show you guys and Connie can show you sheets. Okay, so those are the measures. So the first one is just kind of the basics, like last semester. Look at the measures and see if the groups differ at all. The three groups differ on anything using chi-squares t-test for ANOVAs. You don't have to do very much description of this, just a quick paragraph saying what's in the output. You can actually write it on the bottom. If you write neatly, you can write it at the bottom of the output. Make sure we can read it and we know what it is. Make sure that you annotate the output so when we look through the output we can tell what you're doing. Variables malingering 1 and 2 related to such performance on the TOM test for malingering. Variables labeled malverbal 1 through 6 all relate to scores from the STROOP, another measure for malingering. Put all 8 variables into a Verimax principal component factor analysis. Decide how many factors to keep and save these factors as predictors. Discuss the results. Discuss the results means tell us how you decided which ones to keep. There's no one right answer to this. There's a lot of ways of doing it, so not all of your projects will be the same. We look at them separately and just see if you did a good job of justifying whatever you did. So you kind of look at them together, decide what to do. And conduct a MANOVA comparing 3 groups and the high and low dissociative median split groups. It's a 2-way MANOVA. Common DVs, post-traumatic stress, malingering scale from the DAPS, suicidality, and the factor you save from the factor analysis above. Remember, in the factor analysis, you have to click on Save Scores and save your factor scores. When you do that, go back in and relabel that whatever you're going to call it. With me? Remember, on the principal components analysis, one of the boxes is Save. And then you're going to save principal component scores and factor scores. And that's going to put it into your data file. But it's going to be called FAC1. So we'll have no idea what FAC1 is if you don't tell us what you're calling it. So you just go into the variable view and rename that, whatever name you're giving to that factor. It doesn't have to be the first factor, it could be the second factor, the third factor, whatever one you find most interesting. Output for that one. Again, found. And do the same thing again, but just throw in age as a covariate. Next week we'll show you how to do MANOVAs. Not much more to it. Just put a covariate in the covariate box. And then you've got all the issues to deal with, the assumptions.
And then just put it series.
The third box that says covariates. Now the issue there is that you have to, if we have time today, we can show you how to test the assumptions for covariate with MANOVA. So you have to do all those things we did last time with the models, the IV times the CV, all that kind of stuff. So most of that's going to be just doing it and pointing, putting arrows to the output and telling us what you think is. Did we violate the assumption? When we find out COVA, where the adjustment means, things like that. Select only the simulator and PTSD groups. It's 2 of the groups. Perform a logistic regression with group as the DV and with the association, trauma score, and whatever factor you created, and the lingering tests as the predictors, and take the output, briefly discuss the results. And then finally, the one that we need a little bit more on is perform a regression with impairment as the DV, trauma exposure, association, suicidality as the predictors. And then that one you're going to write an APA-style results section, tables, figures, and a brief discussion. If you spend all your time in the discussion telling us what the study was about and what you found, and there's no discussion, So we want to really grade the discussion process, so try to figure out what does it really mean. If you're giving a talk to a Kiwanis club about this study, what would you tell them it really means? You wouldn't tell them anything about p-values or eta squares. You would tell them what it really means. So see if you can figure out from this stuff. And if you can't figure out exactly, make it up. So just sort of make up something that fits the data, because you don't have a lot of information about the study here. So if you just say, well, I have no idea what you did here, you can just sort of make that up to make it make sense.
So for besides number 6, 1 through 5, when we're discussing, when it says discuss,
Just,
results
yeah, like a
quickly,
paragraph.
You don't want it within a big section
No.
of results.
No.
Just that last one as
Exactly.
results section.
Results section should be a Word document with figures, tables. You don't need to put references in. And then the discussion section after that. And try to make it as close to APA. We don't really take off points if we don't do APA, but you need to learn to do it, so we'll spend time telling you what's not APA. Remember, every figure and every graph has to be self-standing, has to have labels, so the person doesn't have to find out what things mean in the graph by going in the text. There should be no hieroglyphics on there that cannot be found in the note below. And that's an important APA rule. And so that happens to be a good rule. A lot of them are not good, but that is a good rule. So for the 6th one is kind of like last semester's, where you're going to give us a couple of the pages you got of results and discussion. The other ones you can actually write on the output. If one of the two of you has good handwriting, or if you want to type it, it's actually, you can save the output as a Word document, say it saves paper, and then you can type right on there. If you do that, put your annotation in red, right, so we can see it. So we're looking through a lot of these, so we're looking through, we can see what you said. So underneath logistic, when you say what the odds ratios mean, you can put a little thing in red. So we've got lots of points for things like a 1 unit increase in this, for such and such unit in the other, with other things held constant. We'd love to see those kinds of things in there. Those tend to make us want to give you more points.
Yes.
As opposed to, here's the output, you can see what it means. There was a significant logistic. That's not going to get you good points. Okay? Okey-doke. So let me spend a few more minutes showing you the MANOVA. Forgot to load another column here, so I'm going to make up some numbers. All right, so let's rename this as CV. So let me show you a couple of things, the most important ones. So there's really nothing much more to doing the MANOVA, the MANOVA. and then just throwing in the covariate into the covariate box. All right, so that's easy enough. Make sure under options that we have, make sure you have the mean so we get the adjusted means. And the output will look the same, except it'll be, you'll get the covariate in there for significance of the covariate, and you'll get adjusted means for the covariate. So if we look at that. CV was not at all significant, since I just made up some random numbers. Pretend for a minute it was significant. Then we can look at it for univariate and see neither of them even came close. Okay. So that's, everything's the same there. Now when you want to test the assumption though, go into the same idea, but remember you click on model and you do custom and you do the CV times the gender. Let's do the three-way here, treatment, and then you do all three of those. Remember, if you interpret anything else in this output except the one thing, you're making a mistake, right? All we care about is this interaction. And this is the multivariate version of the interaction, and then there's plus you'll get the univariate version of it as well for each of the DVs. So you don't care about the main effect, you don't care about the other any other interaction. This is the three-way interaction with the CV and the two IVs. If that's not significant, that means you've met the assumption of homogeneity of regression. Because if you didn't meet it, what would happen is for each level of the IV, you have a DV, and now what we're having is a composite of DVs and CV. We have it also for, these are for males, these are for females. Complicated this gets. And what we're assuming is this relationship was kind of the same all the way across all of those cells. So if there were a pattern where these were all flat down here and these were slanted up here, then they show up in the three-way interaction, combination of those. I mean, somewhere, if you violated that, somewhere there's an interaction between the covariate dependent variable relationships at different levels of the IVs. And then you gotta, if you do get that significant, you've got to go find it.
How did you do that?
I just, under model, I put in the main effects and the,
Okay, so he's random.
yeah, so I click here.
Oh, wow, okay.
You have to remember to click custom and remember to put in all the individual ones as well as the interaction. Otherwise, it's not a true interaction. So, and you can do that separately if you want. If you wanted to just test one IV, you can do CV by treatment or CV by gender. Don't really break it down. But as long as you don't get a violation, then you're in pretty good shape. Not significant. Homogeneity of regression. Now we're doing it in MANOVA, so we're doing it in the multivariate sense. And the difference is that you get output up here in the multivariate statistics that is putting together the DVs as a latent variable and testing it that way. On this one, this one you want none of them to be significant. So if Roy's is significant and none of the other ones are, it can be a bit of a headache. I guess if any of them were significant, you got some troubles. The trouble with this, remember, for this assumption, the trouble is violations are sort of unpredictable. If you go back to that sheet I gave you earlier, there is a little bit of a guideline for violations. One page we skipped here. That was a good thing to finish up with. So if you go to, in this material, this is some more material on the test criteria, a little bit more detailed in the book, a little bit more on the assumptions. That one you saw already. Go to page, I don't know what page it is. It says 201 in the bottom corner of this page. This is a pretty good guide for both first semester and second semester. I don't know how to get you to the right page. It says 200 in the upper right corner and 201 in the bottom right corner. Right before the MANOVA output starts. Everyone find it? Okay, so this is Stevens again, who does a good job of this. Consequences of violating assumptions of univariate for univariate ANOVA. So just going back to first semester stuff, this gives you a good summary of what happens when you violate assumptions. It's only at the univariate level, so you have to kind of extend that to the multivariate. But if you're looking at univariate violations, this would be a good way to do it. And the good news is that as long as you get equal sample sizes and reasonable size samples, the actual changes in power, what they do is give you the changes in power, the ability to find something that's really there, and the changes in type 1 error, basically, or in alpha violations. So for equivalence, if you look at the left-hand side, they do non-independence, and of course, as usual, that's a bad one. You can't violate that. Non-normality, and skewness with skewness and kurtosis. And it says the actual alpha is less than the nominal alpha when populations are leptocuric, meaning they're too peaked. Actual alpha exceeds nominal for platycuric populations. And that's just for kurtosis. For skewness, it says skewed populations have very little effect on the level of significance or power of the fixed effects model, so just a regular ANOVA. F-test distortions of nominal significance levels of power values are rarely greater than a few hundredths. However, skewed populations can seriously affect the level of significance and power of directional or one-tail tests. You know, remember, we never do one-tail tests, right? Always do two-tail tests. Nobody accepts any publications anymore. So, pretty good news about normality, which we often see ourselves, and you don't have to worry about it too much, even with unequal sample sizes. The skewness has a little bit more effect, and you can see the direction of the effect depending on whether distributions are too peaked or too flat. And then for the unequal sample size, it's a little more complicated. It says effects are slight for alpha, but it can have quite an effect on power for small n's. So you can kind of, if you're doing a proposal and you're dealing with a skewed or kurtotic population, you can kind of make some judgments from this. Then down for homogeneity variance in the bottom, you can see very slight effect for equal sample sizes, but for sample sizes that are unequal means 1.5 to 1 or more. Alpha may seriously affect it. Actual alpha exceeds nominal alpha when smaller samples are drawn from the more variable populations. Let's think this through. So you got two populations. One has a variance of 10, one has a variance of 1. And the one with the 10 is smaller than the smaller number of subjects than the one of the 1. That's going to have a serious effect on the alpha. Actual alpha is less than nominal when the smaller samples are drawn from the less variable populations. So or vice versa. So the moral of the story is don't have unequal sample sizes. They can be, you know, you can have 42 in one group and 41 in another, that doesn't matter. But if you have 42 and 20, then you're going to have some issues with the valid assumptions. And then the same thing for unequal sample sizes. Combined normality and heterogeneous variances, it gets quite complicated. Normality and heterogeneous variances appear to combine additively to affect either level of significance or power. For example, depressing effects on an alpha of leptokurtosis could be expected to be counteracted by the elevating effects of alpha of them in smaller samples from a more variable leptokurd population. So if somehow you get lucky and you have two peaked, but it's the opposite of the small sample size having a larger variance, then they kind of offset each other. But it's actually a nightmare, though, to try and figure out the effects on your alpha level for any of these kind of violations. So you don't want to have too many of those combinations. Usually we don't have that in most of the populations we look at. It's not something. So you can use that kind of to fit into the univariate part of this one when you look at this. Okay. Any questions on any of it? Ready to go? Next time we'll do repeated measures, MANOVA. I think both classes are going to do that. I've got some MANOVA output that we can look at. But what I would recommend, let's see, what do we have for weeks? We have this week and the next week. So for both classes, I would say look at this data by the week after next with your partner. Start thinking about your plan of attack. Maybe do a little analyses, because you're going to have questions. And we won't answer questions about the specific data set, but we'll answer questions about parallel data sets. So some of the questions might be how to do it in SPSS. Some of the questions will be what to interpret. Some of the questions might be just about. Usually, there's a lot of questions about normalizing data, skewness and kurtosis from the first semester. There's a lot of scurrying around those things. So. You don't want to wait to ask those questions till just before this is due or till after the final. It's better to get a little bit of a start so that you can come in and you can spend time going over whatever you need to go over in class. And it's a good review. Yeah, so at least for our final, it's basically a bunch of outputs that you interpret for the whole semester. Connie has some similar, but she has short answers. Everyone prefers multiple choice, but they're actually hard. I know students always prefer multiple choice, but all the data shows us that short answers are getting grades.
When they're taking that many classes, you know, it's hard to retain and think. It's too much.
See, to me,